Okay, this is the last section of 5.3. It's additional properties of the binomial distribution. So we're going to take what we did in section 5.2 and we're going to add just a couple things about the binomial distribution. So we're going to make a histogram, which is relatively straightforward and very easy. Compute this mean and standard deviation, which those two formulas are also on your formula sheet if you look at your formula sheet, and I'll show you that in a second. And then the big one, the application side, is the minimum number of trials, or quote-unquote what we call a quota problem. So to graph a binomial distribution, it is essentially just a histogram idea, and actually more specifically a relative frequency histogram, where we did the percentages or probabilities on the y-axis. So the R values are going to be your horizontal axis, the probabilities are going to be your vertical. It says construct the bars so that it's halfway between, and I'll show you that in a second, and the height corresponds to the probability. So what you'll do, if you look at your binomial table and you find n is 4 and the probability is 40%, you're going to find that you have these 5 possibilities in that table. And all they want you to do is put it on a graph as a histogram. So here's a straight out example of what's going on. When I talked about the 1/2 each direction, basically your bars go like negative 0.5 to positive 0.5. From positive 0.5 to 1.5. So your 1 is exactly in the middle, 2 is exactly in the middle. That's all they want you to do. On the vertical side, you put the probability. So the first one is the 0.1296. The second one and the third one are the 3456. Accordingly, straight across. And then the 0.1536 and the 0.0256. So that's as simple as it has to be. You can do this for any one of them, any n and any p, and that's all they ask you to do. So if I ask you to graph a binomial distribution, that's what I'm asking you to do, is just put all the possibilities onto a graph. A few specifics, things about a graph. If the probability is 0.5, the distribution will always be symmetrical. So if you actually look at your table and go to any 0.5, you're going to see a nice little pattern. It's going to go up and come back down in every single one of them, where the numbers are exactly the same as you go to the left and to the right of the middle number. So that will always happen. And then as you have the probability less than 0.5, so like anything 0.1, 0.2, 0.3, and so on, it's actually going to be skewed right, because most of your probability is going to be less than the middle. As you can see, the dragon tail is going to the right. If the probability is greater than 0.5, so the probability of success is high, it's going to be the exact opposite. You might have probability distributions that kind of look like this, and it's going to be skewed left. So that's kind of some visual things to kind of think about if you kind of glance at the numbers. Alright, back to the binomial idea. If you have a success and failure situation, finding the mean can be a heck of a lot easier than what we did earlier in this chapter. You simply just have to do two simple numbers multiplied together. So if you find this formula on your pink sheet, all you have to do is times n and p together. That gives you your mean in a binomial situation. Also, standard deviation, instead of doing all those complicated formulas, in a binomial situation, you simply can go the square root of n times p times q. So that's very, very easy math as long as you have a binomial situation. So now you guys are probably going to get mad at me, because a flipping the coin idea is a binomial situation. You get a heads or a tails. So if you look at this, n is 4. We're going to flip a coin 4 times. The probability is 50%. What is the expected value, or what we call the mean? Mean is what we call our expected value. And all you needed to do was 4 times 0.5. So I am actually asking the number of heads that will appear. So the probability of getting a head, what's the expected number of heads that we get? 4 times 0.5 is 2. I expect to get 2 heads if I flip the coin 4 times, and theoretically that should make sense. What's my standard deviation? Alright, all you got to do is take the square root of whatever n times p times q is. So in this situation, what do we have here? N times p times q. So square root of 4. P is 0.5. Q is also 0.5 in this problem. So Half of 4 is 2, and half of 2 is 1. What's the square root of 1? 1. So our standard deviation, our spread of the data is 1 in each direction. We'll kind of use that more specifically in a little while. So I guess I just did this problem. Oh no, I didn't do this problem. So a sharpshooter takes 8 shots to a target. She normally hits 70% of the time. Hopefully this is a refresher from the last section. What's the probability she hits exactly 6 times? So we're finding the mean and standard deviation now, not the probability that she's actually going to do it. So if I'm finding the mean, what's her expected value? This is a success or failure because she hits it or she doesn't. All I need to take is the number of times she shoots at it, 8, times her probability, which is 0.7 of a success. We want the probability of a success, and that's going to end up being 5.6 if you multiply them together. And I have this noted down here. 5.6 is not possible, obviously, because you're not going to shoot 5.6 bullets or whatever you're shooting at a target. You know, you got to do 5 or 6, but it is okay because we're just saying what's the expected number of times she hits the target. I expect her to hit the target 5.6 times out of 8. Okay, so she might hit it 5 or 6 times. What's the standard deviation? I just got to go square root of 8 times 0.7 times 0.3. So if you can just multiply that out, I got to find my calculator, I haven't done that yet. 8 times 0.7 times 0.3 equals 1.68, but I got to take the square root of 1.68. Square root of the answer, 1.296, or 1.3, I guess if you want to round it, would be my standard deviation. So my spread of my data, I give or take 1.3 times. Alright, so that's the simple, that's a heck of a lot easier than what we've done before. Okay, moving on to the quota problems. This is the main application of a binomial distribution. So what exactly is a quota problem? It's basically finding out the minimum number of trials, or essentially n, because that's what we're going to end up finding. I want to find n for a given probability, a given situation. So solved when using binomial probability, obviously we need a success or failure. That's the only way this works. We're going to use the table that you're given, the binomial table, but we're going to use it kind of working backwards. In these cases, we know your R and your P. So we know the number of successes we need. I know the probability of a success, and that's basically it. And it's going to be kind of a game to work backwards to figure out the smallest number n that satisfies our requirements. So basically what will make this a little bit easier to do is I want to use it in equivalent formula. So what you're going to be doing is I'm going to be giving you a probability of at least 1 or at least 3. We want at least, and that's going to be how it's phrased. But that's not necessarily simple to add up everything that's greater than it. So we're going to use the complement idea. If I phrase it that I want at least 1 success or get at least 1 thing, I'm going to use the complement and say, you know what? I only want to focus on the probability of less than 1, which is just the probability of 0. The reason this is beneficial is I only need to focus on 1 number instead of, if I end up getting that n is 15, I would have to figure out what 1, 2, 3, 4, and so on all the way up to 15 is. Or I can just look at 1 number, and it's a lot easier. When you don't know n, it's going to be a lot easier to do this complement idea. So if I phrase it that I want at least 2 successes, then it's everything less than 2. So that would be 1 minus the probability of 0 and 1. Contrary, if it's, you know, I want something that's at least 3, then I go less than the 1, 2, and 3, or 0, 1, and 2, I would subtract from 1. And here's your general thing. Basically, whatever R is, or the M, or whatever, you know, your 3, you just add up the stuff that's less than it. So let's kind of dig in here and let's see if we can figure out how these work. So let's say a certain information service is a business of finding addresses of long-lost friends. They claim to have a 60% success rate. Right there, I know that's my P. If whatever they claim it is, that's what it's going to be. Suppose that you have names of some friends whom you have no addresses and decide to use this company and track them down. how many names, so here's the quota problem, how many names would you have to submit to be 90% sure that at least 3 addresses will be found? Notice the at least 3 showed up, so that's why I kind of wrote this here. I want to figure out the probability that the number of successes I have is greater than or equal to 3. Now what percent is this? I need this percentage in your table, alright, to be greater than the 90%. So I want to be 90% sure. And how this works is you would have to go in and figure out and look at each individual R and add them up till they get higher than 0.9. Well, that's kind of frustrating. So this is a little bit easier. Instead of going 3, 4, 5 and adding all them up, I want to do the complement idea. So this situation right here, probability of R greater than or equal to 3 that we just showed you on the last page, would be exactly the same as writing this. 1 minus the probability of 0, 1, and 2. So I'm only going to focus on 3 things. Also must be greater than or equal to that 0.9. Alright? So that hopefully makes sense to being the exact same thing. Instead of looking at 3 and above, I'm going to subtract below 3, 0, 1, and 2's probabilities, and hopefully that's still greater than 0.9. So going back to this is more written out for you if you want to try read it. I need to go into my table, and I know I kind of give it away that n is 7. You would have to literally guess. This is a game. And a lot of times what I try to show you is if these 3 subtracted from 1 need to be still less than 0.9, or essentially greater than 0.9, this number, I want to go in and figure out when these are added together, these things need to be less than 0.1 because I need to be greater than 0.9. So I need to go in and look where P is 60%. So you need to go to your P is 60% column, and you can just start looking at the first 3 at 0, 1, and 2 and add them up. The first time as you go from n is 2 and up that they do not add up more than 0.1, that's your answer. So for instance, if you look at, just for argument's sake, n equals 6 at the 60% category, you would end up having 0.004, you would have 0.037, and you would have 0.138. And that obviously adds up more than the 0.1. So n equals 6 is not good enough. So we would then have to move on to n equals 7. And at n equals 7 at that level, you have 0.002, 0.017, and 0.077. And if you add those up, it is less than 0.01. Because what is that? 14, 6, carry the 1, 9. So it's like 0.096. That's less than 0.1. So when I go 1 minus, okay, when I go 1 minus all 3 of these, I am still above my 90%. So that would be the lowest number n, is kind of how they phrase it, or my best answer. I would need to give 7 names, 7 values to be 90% sure they would find at least 3 of them. Alright, I know that gets a little bit tricky. We will definitely do a couple more of these problems in the homework before you probably even work on your homework in class. So here's the assignment we'll look at. You might want to try look through some of them, or maybe try a quota problem before we come to class. And hope you guys have a great day.